In this video, we're going to learn RAG from beginner to advanced. It has two labs, Lab 1 and Lab 2. In Lab 1, we're going to talk about Retrieval-Augmented Generation. We are going to take a look to a RAG pipeline. We're going to learn what is a retriever and what is a generator. We're going to talk about vector database. We're going to learn what is a vector database. We're going to talk about embeddings. We're going to see the difference between vector search versus semantic search. Then we're going to move to the second chapter. We're going to talk about 3 types of chunking techniques. We're going to learn what is fixed size chunking. We're going to talk about LLM-based chunking, and also we're going to talk about semantic chunking. After that, we're going to get our ends data. On chapter 3, we are going to build our first embedding pipeline and retrieving pipeline. On chapter 4, we're going to talk about query decomposition. On chapter 5, we're going to talk about multi-vector retriever, and on chapter 6, we're going to talk about contextual compression retriever in order to remove noise in the data. On chapter 7, we're going to talk about metadata filtering. After finishing lab 1, we're going to move to the second lab. We're going to talk about types of RAG architectures. Then we're going to move to the chapter 1. We're going to talk about naive RAG. We're going to learn what is naive RAG and how it works. Then we're going to move to the second chapter. We're going to talk about advanced RAG techniques. We're going to talk about Agentic RAG. We're going to learn what is Agentic RAG, and we're going to learn how to implement it. Then we're going to move to the second point. We're going to talk about adaptive RAG. We're going to learn what is adaptive RAG and how we can use it in order to build systems that choose the best path in order to respond to the user input. Then we are going to move here to another point where we're going to talk about adaptive RAG with self-reflection. We are going to build systems that reflect, that revise its own outputs. And yeah, that's all we're going to learn throughout this video, guys. Now, about prerequisites, you need only the basics of Node.js and LangChain. Let's get started. So, what is RAG? RAG is a technique that allows to enhance model generation by providing the model the ability to get access to external data sources or internal data sources. That is the definition of RAG. RAG is a technique that allows a model to get access to internal and external data sources because these LLM are limited. They don't have access to external data. RAG is there to augment this LLM. It's like a tool that we're going to add to the LLM so that the LLM can have the possibility to get access to external data. You can see on this diagram in here, guys, we have LLMs. Now, when they train LLM, they train it on a huge amount of data so that LLM becomes genius. If we ask an LLM a question it was trained on, like what is JavaScript, it knows everything. What is Python? What is x plus y is equal 0? Find the value of x. It knows the answer because the LLM was trained on a huge amount of mathematical books. So what if we ask the LLM about something it wasn't trained on? Like what are trending now in tech? The LLM is gonna fail. If we ask again, what is the current weather in Miami? The LLM is gonna fail. It doesn't have access to the internet, and also it doesn't have access to internal data. For internal data, we have enterprise data, or it can be my own data. If I ask the LLM about something located in some PDF, it's gonna fail. It doesn't know anything about my PDF. Or if I have enterprise data in a MongoDB database, I try to ask the LLM body, it's gonna fail. It doesn't have access. Now, these are kind of issues RAG tries to address because LLM doesn't have access to internal data and external data. Now, with RAG, we're gonna give the LLM the possibility to get access to internal data or external data. These are the advantages of RAG. It allows to augment the LLM. Now, we are going to take a look to a RAG pipeline. You can see in here we have a little diagram. I'm going to explain you how it works. Now, when building a RAG system, we have to consider 2 steps. We have here the first step, which consists of data storage or data indexing. We have to take the data, it can be books, PDF, and then we're going to keep it inside a vector database. Now, we have here the second step, where it consists of retrieving data from a RAG system. Now, in here, guys, before we keep the data in a RAG system, we have to run through some steps in here. Now, you can see in here we have documents. We have to gather documents. We have to put in place books that we want to put in a RAG system. Now, in here, you can see we have here documents. We are going to take this document, we're going to pass it to a text splitter. So, what is a text splitter? A text splitter is basically a function that allows to split, that allows to convert a document into multiple chunks. You can think of a tool that allows to cut a document into multiple pieces. And then once we have here these pieces, we are going to take them, we're going to pass it to an embedding model. So what is an embedding model? An embedding model is a model that allows to convert these chunks into embeddings. Embeddings are basically numbers. Now, why should we split our documents into multiple chunks, multiple pieces? Now, every LLM has a context window. Context window is a amount of data the LLM can process in one go. Let's say the context window of this LLM right here is 32k tokens. Okay. Now let's be in a situation where our documents, the number of tokens is 50k tokens. Now, if we try these 50k tokens, we try to pass it to the LLM here. The LLM is gonna fail to process the data. We're gonna get an error, guys. It's gonna fail. It goes beyond the thresholds. So in order to avoid hitting the thresholds of the LLM, we are going to split the data, let's say in chunk of 1k. And then we're gonna take this 1k, we're gonna pass it to the LLM, and then the LLM is gonna be able to process it, and then we're gonna get here embeddings. Embeddings are basically numbers, as I said previously. Now, once we have here these embeddings, we're gonna take these embeddings and then we're gonna pass it to a vector database. A vector database is a database that allows to store data in vectors in numeric way. Okay. Now, once we have data, we finish working on the data indexing step. We are going to move to the second step where it's time to query our vector database. It's time to retrieve data from our vector database. We can try to chat with our system. Now, in here you can see we have here the LLM. Okay, we have here first of all, we have here the user. The user makes a query, create a query, and then pass it, forwards it to the LLM. And then the LLM has a tool, a retrieving tool. It's gonna call this retrieving tool, and then it's gonna take here, you can see we have here the LLM, it's gonna forward the user query to a retrieving tool in order to retrieve the data from a vector database. And once it gets data, it's gonna return here chunks of documents because data was stored in chunks in a vector database. It's gonna return here chunks of documents, and then we're gonna take these chunks, we're gonna pass it to the LLM as context, and then the LLM is gonna generate a response to the user. That's how a RAG system works, guys. Okay, you just understand how a RAG system works. Okay, it's pretty simple. Okay. Now we are going to take a look to some components of a RAG system. So a RAG system is composed of two components. We have a retriever and a generator. So what is a retriever in a RAG system? A retriever allows to retrieve data from a vector database. You can see here, we're going to take a user question, and then we're going to embed it. First of all, we're going to embed it so that we can perform similarity search in vector database. And then we're going to have your data. We're going to have a chunks of books, chunks of documents. Okay, that's how a retriever works. A retriever, it basically retrieves data from a vector database, nothing else. That is the job of a retriever, to retrieve data in a vector database. Now we have here a generator, which is the LLM. The role of a generator is to generate a response to a user. Once we retrieve data in a vector database, we are going to take these chunks here, and then we're going to pass it to the LLM in order to have here an answer. Yeah, guys, you have to put that in mind. A RAG system has two main components, a retriever and a generator. Put that in mind. Now we're going to talk about vector database. As said previously, a vector database is a database that allows to store data in numerical way. You can see here we have a document. We are going to take the document, we're going to pass it to an embedding model, and then we're going to convert it into embeddings of vectors. And then we're going to take these vectors, these digits, we are going to pass it to an embedding model. This data is stored in a vector database. Data are stored in embeddings, okay? These dots right here are numbers, okay? Now, when dealing with a vector database, we have here two types of search. We have vector search and semantic search. A vector search is a technique that we use in order to find data in a vector database by using vectors or embeddings to find similar data. Let's say we have here a data. Let's say I have here Apple. Okay. We are going to take Apple, this word, we're gonna pass it to an embedding model right here, and then we're gonna get here embeddings. I'm passing 1, 2, and here we're gonna get here 3. Now we take here banana, we take that, we pass it to an embedding model, and then we're gonna get here again vectors. I can have here 1, and then here 1 again, and then here 3. Now, in order to find the data in a vector database, we can use a vector search. Now, we are going to, once a user is right here, makes a query to our system, we are going to take the user query. Let's say the user query is looking for Apple. The user pass here Apple right here. We're going to take Apple. We are going to pass it to an embedding model here. And then once we pass it to an embedding model, we're going to convert it into embeddings. Maybe we can convert it again into 1, 2, and then here we're going to get here 3. Now we are going to use here these embeddings in order to find similar data. Let's say we can get, we are going to return here chunks of doc. We're going to have here Apple and banana. You can see in here we have, in Apple we have 1 here, we have here 2, and here 3. And in banana here, we have here 1, we have here 1 again. Yeah, we have here 1 and 3. Let's say the vector database can return here Apple and banana. And that's how vector search works, okay? We use these embeddings in order to find similar data in a vector database. You can see in here, we pass here word coffee. We are going to convert it into embeddings. And then in here, they can return data that is the same vectors, okay? They can return here or chocolate, coffee, latte, or tea, okay? That's what we call vector search, okay? It's a technique that uses numerical embeddings or vectors to find similar data, text, images, and audio, okay? Now we have here semantic search. Semantic search is about finding data in a vector database by using the meaning, the intent behind the user query. You can see here, guys, we have the vector database. Now the user pass here query, find me a warm drink. Now we can use here the similarity search in order to find data in a vector database by using the meaning of the query, okay? First of all, we pass this query to an embedding model to convert it into embeddings, and then they're gonna perform here similarity search. Okay, they're gonna use the meaning. Okay, and then the system can return all chocolates, coffee, latte, or tea. Okay, that's how it works. Okay, and you can see here pass here orange, apple. These data here are represented in vectors. Okay, you have to know that. Now you can see here again, we take here document and the user forwards a query like how do I reset my password, and then we're gonna forward it to a vector database, and then they're gonna perform similarity search, and then they're gonna return here vectors. Okay, they're gonna perform similarity search in order to get data. Now we are going to talk about some vector database here. We have here Chroma. These are vector databases that we can use when building a RAG system. We have here Chroma, Vespa. We have here Keydrant. We have here Pinecone, Weaviate. We have here Redis, and Postgres. These database here supports vector database. Okay. Now in our case, we're gonna use here Pinecone. Okay. That is the vector database that we're gonna use throughout this video. Okay. Alright guys, now we move to the second chapter where we're going to talk about 3 types of chunking techniques. You can see previously here guys, we talk about splitting a document into multiple chunks. If I move here, you can see we have a text splitter. And here we use chunking techniques in order to split a document into multiple chunks. Now we're going to learn some techniques that we use in order to split a document into multiple chunks in order to keep the meaning. Now I'm gonna scroll at the bottom, and then we're gonna talk about these different types of chunking techniques. Now in here we have our first technique, which is fixed size chunking. So what is fixed size chunking? Fixed size chunking is a technique that takes a document and split it into a fixed size without considering natural breaks or the structure of the content. With this technique, we lose the contents of a chunk. Let me explain how we lose the contents of a chunk. Now, in here you can see we have a document. We have here, hello everyone, my name is John. And then here we are going to take the document, we're going to pass it to a text splitter. As I said previously, a text splitter is a function, is a tool that allows to split a document into multiple pieces. Now we're going to end up with something like this. We're going to have here for the first chunk, we're going to have here hell. For the second chunk, we're going to have here LO and here every. For the third, we're going to have here one. And here we're going to have here my name. Okay, we don't have here E. And here you can see for the last chunk here, we're going to have here E is John. Okay, you can see for each chunk here, we are losing the meaning. For each chunk, we lose the meaning. I don't understand what is the meaning of hell. I don't understand the LO error. If you pass this to the LLM, even the LLM, it's going to lack the context. Now, how to mitigate to this kind of issues of fixed size chunking? Now, in order to mitigate to these kind of issues, we are going to add a feature to fixed size chunking. You can see this is fixed size chunking. Okay, with this technique, we lose data. Now it misses a feature. Now I'm gonna add a feature on it in order to preserve the meaning for each chunk, which is chunk overlap. Okay, that's what we're gonna add to fixed size chunking technique in order to preserve the meaning. I can call this is a feature that we just added to fixed size chunking. Now with this technique, we take a piece of word from the next chunk. You can see this is the first chunk here, this is the second one. Now we're gonna take here a piece of the second chunk. We can take here LO, and then we're gonna have here LO. And right here, let's say we have here something like LO and here every. Now we're gonna take here a piece to the first chunk. We can pass it here. We're gonna have here everyone. Okay. Now we're gonna have here one, and then we're gonna have here everyone. And again, for the third chunk here, we're gonna take again a piece from the fourth chunk here. We're gonna have here now right here. We're gonna have something like this. Let's say if I add here E, we have the name. And we can take like this is. You can see right now here we have my name is. Okay. Now you can see with this technique we just added the context to a chunk, and then for the last chunk it's gonna stay like this. That's what we call chunk overlap. With chunk overlap, it allows to augment the meaning of a chunk. You can see in here again we have here now the documents. Hello John. Can you explain to me what is a vector database? Now we take it, we split it into 4 chunks again in here. And then here we're gonna have hello John. Can. Now we take here, from the next chunk, we take can, we pass to the previous chunk in order to augment the meaning. We have the hello John can. Now for the third chunk here, we are going to take explain, we pass it to the second chunk here in order to augment the meaning, and then we're gonna have here can you explain. What if we have here, can you? We don't have the meaning. Now, in order to improve the meaning, we take here, explain, and we pass it to the previous chunk. And then for the last chunk here, again, we take here, what is, we pass it to the first chunk. And then we increase again the meaning. If we get rid of what is, we're going to stay with explain me. But what if I pass here what is? You can see with chunk overlap, we augment the meaning of the chunk. Okay, that is the benefit of using chunk overlap. When we're gonna make a practice, you're gonna understand that pretty well. Right now, we are surfing the basic. Okay, I want you to get a basic. Now, let's talk about LLM-based chunking. So this technique allows us to use LLM in order to split a document into multiple chunks. This is pretty advanced, guys. And in order to use this, you have to pay a model provider for that. For the first one here is totally free, and we can enhance here the fixed size chunking with chunk overlap in order to get good results without paying anything. But for the second one here is pretty advanced, and here you have to pay something to the model provider. And here you can see we have here documents. We're gonna take these documents, we're gonna pass it to the LLM. Then the LLM is going to split it into multiple chunks. And once we have a chunks, we're going to pass it to the embedding model in order to get embeddings that we're going to pass to a vector database. And for the last one here, before we start with the practice, we have here semantic chunking. This one here is to take a text and divide it into meaningful units, such as sentence or paragraph, which are then vectorized. For this one too is pretty complex, okay? For this one too, we can use LLM for that, okay? Because it's pretty complex. Yeah, in order to keep the meaning of a sentence, you have to use a system which is pretty smart for that, okay? For this one too, we can use the LLM. Now we're gonna start with the practice. We're gonna get our hands dirty, okay? We're gonna start with the practice. Now we're gonna move to the third chapter. We're gonna build our first embedding pipeline and retrieving pipeline. Alright guys, now we're gonna learn how to build an embedding pipeline and a retrieving pipeline. So before you keep going, you're gonna set up our Node.js project. To set up our Node.js project, you're gonna head into your terminal. You're gonna tap make there in order to create a folder where you're gonna work on. And once you finish creating a folder, you're gonna install this package in order to be ready, okay? Now you're gonna install Decomposition in order to get access to our environment variable. You're gonna install LangChain, or if you want to, you can head on LangChain.com, and then you're gonna type here this command npm install LangChain. Once you finish, you're gonna install here Pinecone package. For the database, for a vector database, we're gonna use Pinecone. And in order to extract data from a web page, we are going to use Cheerio. Cheerio is a web-based loader. You're gonna type this command. Or if you don't wanna do all of this, you can just go head on the GitHub repository of this video and then clone it, and it's gonna help you to follow along this video. Now I'm going to head into in here, guys. We are going to head into in here. Okay, we're gonna create here a file embedding pipeline, and I'm not heading. And here I'm going to import here some package that I want to work with, okay, like documents. We're going to import here the recursive character splitter in order to split a document into multiple chunks. We're going to import here Cohere embeddings. Cohere embeddings is an embedding model provided by Cohere. We're going to get a key of it. You know, as I said previously, guys, let me go back inside in here, and you can see in here, in order to extract data from, once we finish extracting data from a web page, we need to take these chunks, and once we take these chunks, we need to pass them to an embedding model in order to get embeddings. Now for an embedding model, we're going to use an embedding model provided by Cohere. Now you're going to head on cohere.com and create an account if you haven't already, and head into API key. You're going to copy here the API key. Once done, you're going to head into your data file. You're going to pass here the Cohere API key, and also you're going to pass here your Pinecone API key. Now in order to get your Pinecone API key, let me show you what you're going to do. I'm going to click here, Pinecone. I'm going to head on my Pinecone dashboard, and you're going to head into database, and you can see in here we have indexes, and indexes are database. Now head in and click here, create index. And once in here, you're going to pass here the name of your database. Once you pass here the name of your database, you're going to click here, create index. Okay. Now, in order to get the API key, you're going to head into API key. Okay. And you're going to create here an API key. You're going to copy it, and then you're going to pass it in here. You're going to pass here your Pinecone API key, Pinecone index. For the Pinecone environment, you're going to let it empty. Okay. Now, once you finish, we're going to get an API key for a model provider. Now, for a model provider, you're going to use Cerebrus. Now, if I type here Cerebrus, let me pass here Cerebrus. I'm going to click here, and you're going to create an account if you haven't already, and then you're going to get an API key, guys, okay? Get free API key. Click here. Then you're going to get an API key provided by Cerebrus, okay? Do that, okay? You're going to head into inside API key, and then you're gonna copy an API key. Okay, done. Once done, we're gonna go back inside text editor, and we're gonna start coding. Now in here you can see I've already imported here Pinecone and Pinecone clients, and here I import to Cheerio web-based loader, and we import here Decomposition in order to get access to our environment variable. Now what I'm going to do in here, guys, I'm going to create a function doc embedding. We're going to pass it a URL because we are going to use Cheerio web-based loader. If I pull my cursor over the Cheerio web-based loader package, you can see in here, guys, it takes a web URL. it takes a web URL, and then I pass here loaded the load, and then we're gonna get here an array of documents. Now we are going to pass here, this is the web URL that we're gonna extract the data, and then here I pass here Studio web-based loader. We're gonna have here an array of documents, and once we have an array of documents, I'm gonna iterate through. I'm gonna add metadata. You know, we can use metadata in order to add filtering from the vector database. Now I'm gonna get into the details about metadata later. Okay, now in here I pass here doc with metadata, and then I add here metadata of the URL, okay? Because we can use it in order to make filtering. And here I'm gonna pass here recursive character splitter. Pass the chunk size of 1000 and chunk overlap of 200. And then here we're gonna pass here all splits, text splitter, and we are going to pass here the document in order to split it into multiple chunks. Okay, we pass here text splitter, and then we invoke a function here, split documents. Okay, now we're gonna pass here cohere embedding model. Now we are going to take these chunks, we're gonna convert it into embeddings. Now we are going to pass here now Pinecone. As we already generate embeddings, now we're gonna take these embeddings, we're gonna pass it to a vector database. And then you can see here we instantiate Pinecone clients, and then we pass here these embeddings. You can see new Pinecone store, and then we pass here these embeddings. Okay, guys, and here we're gonna pass here console.log finish embedding. Okay, now when we're gonna run this pipeline, we're gonna extract data from this web URL, and then we're gonna put it in the vector database. Okay, that's what we're gonna do. Now what I'm going to do, guys, I'm gonna head into the console here, and I'm going to run this pipeline. I'm passing node source, and then we are going to run the name of, we're gonna pass here the name of the pipeline, and pass here embedding pipeline like this, pipeline like this, the JS. Okay, yeah. And now I'm gonna run this pipeline, and then we're gonna embed the data. Now we're gonna run this pipeline, and then we're gonna index the data. Now you can see, guys, we console here finish embedding. It means we finish storing the data in a vector database. Now we're gonna create a retrieving pipeline in order to retrieve data from a vector database. Now in here I'm gonna import all needed package. We import here cohere embeddings, Pinecone store. Then we're gonna create a function query vector db. We're gonna pass here the query, and in here I'm gonna pass here cohere embeddings. Once the user provide the query, we're gonna convert it into embeddings. Then here we pass here Pinecone clients, and here we pass the Pinecone index here, and then we create right here Pinecone store that from existing index we pass here embeddings, and we pass here the Pinecone index. And then here we invoke a function similarity search. Okay, we're gonna perform a similarity search in a vector database in order to get data. Okay, and once we get data, we're gonna return data. Now I'm gonna try to code a function, and we're gonna see what we're gonna get. Now we're gonna pass here const. Yeah, we're gonna pass here const result is equal to query vector db. I'm passing query vector db, and here I'm passing here query. I'm passing types of prompts engineering. Okay, now once we pass this, we're gonna get data. Let me const the data here. We're gonna head into the console, and we're gonna try to run this to see if we're gonna retrieve data. And we're gonna pass here retrieving pipeline. I'm passing retrieving, yeah, you're gonna pass here retrieving pipeline. Okay, like this pipeline, like this the JS, and then we're gonna get data. Okay. And yeah, guys, so you can see actually we have here the data. You can see we have here prompt engineering, also known as encounters prompting. Okay, now if we scroll a little bit here, you can see that actually we got only the definition of prompt engineering. Okay, and our question was types of prompt engineering. We got false data here. Okay, yeah, you can see we don't have what we want. We don't have what we want, guys. Now, let me show you how we can generate the response first with the AI, and then we are going to move to the fourth chapter where I'm going to show you how to transform the user query so that we can improve the retrieval. Okay, we're going to talk about query decomposition and query transformation. Okay, using step-back prompting. Okay, now let me show you first how to do generation. Now, and here what I'm going to do, guys, I'm gonna import here prompt template and chat prompt template. Okay, I'm gonna create a prompt, And here you can see here's the prompt. You are an assistant for question answering task. Use the following pieces of retrieve context to answer the user question. If you don't know the answer, just say that you don't know. Use phrase sentences maximum and keep the answer concise. And we're going to pass you the user question and we're going to pass you the context. Now what I'm going to do, I'm passing chain. We pass you the prompt, generate response, and then pass it that pipe. We pass here the LLM is right here. I'm going to use ChatGPT. And right here, we are going to do something like this. I'm pass here an input. We're going to pass here the question. And for the user question, I'm going to take it and pass it into a constant. Pass here question like this is equal to this. Okay. Now I'm going to pass the question. And I'm going to take here the question. I'm going to pass it right here like this. And we're going to pass here the context. The context is the retrieve data context like this. Now what I'm going to do, you can see in here, if we head into the console, we are getting back here an array of documents. Now what I'm going to do, I'm going to convert it into a string. Okay, I'm going to serialize it into a string. Now I have a function. Yeah, I have a function right here. I'm going to copy it and then I'm going to pass in here. Okay, here's the function I'm passing here. Format document is string. And I'm passing here const doc to string like this, and then is equal to this. I'm gonna pass here the results. We are going to take here the results, and then we're gonna pass it into the function. Okay, format document and string like this. Now I'm gonna take this string and I'm gonna pass as context to the LLM. Okay, like this, and then I pass here console.log, and I pass here AI response. Okay, let's see what we're gonna get in here. Now I'm gonna head into the console again. And now I'm gonna run this. Let's run this again. I'm gonna run the file node source retrieving pipeline, and let's see what we're gonna get here, guys. And yeah, you can see here we have the response of the AI. The context provided does not explicitly mention specific types of prompt engineering. Okay, you can see the AI says the retrieved data does not align with the user question. That's what we got. Now, in order to mitigate to this kind of issue, we're gonna use here a technique query transformation. Okay, now I got a prompt here that I'm gonna use in order to transform the user query. Now I'm gonna take it in here. I'm gonna copy it right here. We got a prompt right here. I'm gonna copy that, and then we're gonna pass it in here. I'm pass at the top right here. Okay, query yeah, you can see query transformation. I'm pass here transformation prompt. You are an expert at query writing for semantic search retrieval, augmented generation. Step back and think about the users in the line intent before rewriting the query. Instructions: analyze the original question, identify the core concept and implied context. Generate at least 3 alternative written queries that better express the semantic intent. Okay, guys, in here I'm using step back prompting. Okay, in order to transform the user query. Now we're gonna try to do that. Now let's use this prompt right here in order to generate 3 alternative questions. Now we're gonna pass the LLM with structured output, and I'm passing z.objects. I'm using Zod, guys. Type npm install in order to install Zod. And right here you're gonna pass here z.array, z.strings, and I pass here describe array of questions for semantic search retrieval. Then we are going to pass here the prompt query transformation pipe, and I'm using a runnable. A runnable is when we take an output of a function and we pass it as an input to the next function. Okay, that is a runnable. Now I'm passing query transformation prompt pipe, and then pass here structured LLM, and then I'm passing here chain.invoke, and here I'm passing the question. And now let's see what we're gonna get in here, guys. I'm passing console.log, and I'm passing gen questions. Now let's see if we're gonna get an array of questions. I'm gonna head into here. I'm gonna run here this file, and we're gonna get here an array of questions. Let's wait a bit. Yeah, you can see, guys, that actually we got here an array of questions. You can see what are the different types of prompt engineering techniques. You can see we have here again types of prompt engineering methods, prompt engineering approaches, and the applications. Okay, you can see the LLM rewrite the query, transform the user query for better retrieval. Now what I'm going to do, I'm going to use here these questions in order to have the response. Now what I'm going to do here, guys, I'm going to move here. Right now I'm going to call here, you can see pass query vector db. We're going to take here the response. I am going to uncomment this in order to format, in order to serialize the array of documents into a string, and then I'm going to call the function. And here what I'm going to do, I'm going to iterate through the array of questions. Okay, now I'm passing here, and I'm passing here for, let me just pass here. Look, you can see here we got a string here. You can see questions. Okay, this array. Now I'm going to do something like this. Let me see the tab here. Okay, we have here generated question. I'm passing here generated questions. I'm gonna copy that, and here is equal to questions is equal to generated questions, that's questions. Okay, like this. And now I'm gonna iterate through the questions array. I'm passing 4. Now I'm passing 4. I'm passing const question of questions. Okay, and actually we got here questions. Let's see at the top here. You can see I should pass here query. I'm passing right now query, and I'm taking the query. It's gonna be the user input. I'm passed there, and now we're gonna call that function right here. Let me see. I'm gonna copy the function, and then what we're gonna do, guys, we are going to pass in here like this. Okay, and I'm gonna copy the question and pass it in here. Okay, and here we're gonna create an array and pass here retrieved docs is equal to an empty array. Now once we have here an array of documents, we're gonna take it, we're gonna push it inside the retrieve doc array. I'm gonna copy that, and then pass it here, that push like this, and then pass here the results. Okay, like this, guys. Now I'm gonna pass here flatted docs. Okay, flatted docs, I pass the retrieve docs, the flats. Okay, and now I'm passing another constant. We're gonna pass another constant flatted docs to string. Okay, to string, because we're gonna get here an array, and I want to serialize that array to string. Now I'm gonna call here the function right here. I'm gonna take this right here. Let me comment this line right here. I'm gonna copy this, and then we're gonna pass in here. We're gonna pass the flatted docs to strings. Okay, like this. And now what I'm going to do next, guys, you can see we have here the LLM, pass here chain 2 like this, and I'm passing generate response prompt. Okay, this is the prompt, and I'm pass here underscore. I'm pass here prompt like this, generate response prompt. We're gonna use this we're gonna use this prompt in order to generate the response. Now I'm gonna take that and pass in here, and now we are going to do this. We are going to pass the flatted docs to string. We're gonna pass it as counters. Okay, we're gonna pass it counters, and here we're gonna pass the user query. Okay, like this. Okay, and then we're gonna get here the A response. Now let's see what we're gonna get. And we should pass it chain 2 and pass it chain 2 like this. Okay, now let's head into the console and run this and see what we're gonna get, guys, is the response generated by the AI. And now I'm gonna run this again, and let's see what we're gonna get. Actually we got an error, guys. You can see question isn't defined. And now let me see, we have a question, and here I'm going to move here. Let me check here and what we got in here. We should pass here question and counters, but actually question is undefined. Let's see. You can see pass here question. Okay, question, and here pass here query. Let's see on which line we got an error. You can see chain. Here we have an error. Okay, now I'm gonna pass here the query, the user query. You can see I modify here the user query, the user input to query. You can see we have a query. We should pass here query. Okay, like this, and pass here query. Like this. And now let's run this again, and we're gonna get data. Okay, I'm gonna run this again. You can see, guys, that actually we have here data. You can see the types of prompt engineering include zero-shot prompting, few-shot prompting, chain-thought prompting, self-consistency. Okay, you can see actually we have here data, because the LLM create multiple versions of the user inputs. And let's say I want to run this again. Let's try to see if we're gonna get data. And I'm gonna try to pass here. I'm gonna console here. I'm gonna pass here console. Yeah, we're gonna console.log, and then we're gonna pass here the generated query. We're gonna see what we're gonna get back from the LLM. Okay. Now, once the LLM generated question, we're gonna see that here. Okay. Now I'm gonna run this again, and let's see. Again, you can see what are the different types of prompt engineering techniques. Types of prompt engineering. Yeah, you can see actually the LLM generate multiple versions of the user inputs. Yeah, we got data, but sometimes we may miss data because sometimes the LLM can generate a query which doesn't align with the user document, doesn't align with the vocabulary of the document. So we may miss data, guys. Now, in order to mitigate this kind of issue, I'm gonna introduce you to another types of retrieving techniques. We're gonna talk about now multi-vector retrieval. Okay, this technique is much efficient than this naive retriever. With this one, we may miss data, guys. We may miss data, even though you can see we use here the LLM in order to generate multiple versions of the user input. We may miss data, and you can see in here, guys, we have here a little context. Yeah, we don't have everything about prompt engineering. You can see the context is pretty low. Now, in order to have a bigger context, I'm going to use this technique right here that we call multi-vector retrieval. So what is multi-vector retrieval? Multi-vector retrieval is a type of technique that allows to create multiple embeddings of a document. You can see in here, guys, we have here a document. Okay, we're gonna take it, we're gonna pass it to a text splitter, and then we're gonna split it into big chunks that we're gonna call parent chunks. Now, in our case here, when we create a naive embedding pipeline, you can see we take the document and then we split it into a chunk size of 1000. If we want to create a big chunk, I can pass here even 4000 or 3000. And then that's what we're gonna call parent chunks. You can see in here we have parent chunks. Now, once we have here this big chunk, I'm gonna take it again. I'm gonna split it into smaller chunks. That's what we call child chunks. And then we're gonna create a UUID. We're going to create an ID inside these child chunks. And we're going to create also an ID for the parent chunks. And then we're going to, from the child chunks, we're going to make a reference from the parent documents, okay? And now we're going to take the parent chunk and these child chunks. We are going to take it, we're going to pass it to the embedding model. We're going to create embeddings, and then we're going to take these embeddings, we're going to pass it to a vector database. Now, this is how we create a multi-vector retrieval. If you want to retrieve data, here's how we're going to process. We have here the user. We're going to forward a query to our system. We're going to retrieve here smaller chunks. We can retrieve small chunks here, let's say 3. And then as these small chunks has a reference to parent chunks, we are going to use here these small chunks in order to retrieve the parent chunk here. And then we're going to take this parent chunk. That's what we're going to pass to the LLM, okay? This is how it's going to work, okay? It's pretty efficient, guys, okay? With this kind of technique, we may improve the context to the LLM, okay? Let's see how it works. I'm going to head into here, guys. And now I'm going to create here file multi-vector retriever. Multi-vector, like this, retriever. Okay, like this, .js. And what I'm going to do, I'm going to copy everything inside the embedding pipeline. Let me just copy here this package and then pass it in here. Okay, now I'm going to create a function. I'm going to name it load raw docs. We're going to use this function in order to extract data from a document. And you can see we pass it an object. The UROs, this is an array, and the doc ID, okay? Now, why I pass here the doc ID? You know, guys, we are going to use the doc ID in order to retrieve data in a vector database. Let me explain you. Now, if I head into the retrieving pipeline at the bottom here, I'm going to create a doc. Now, this is the structure of a document. Yeah, you can see in here, a document has a page content and also it has metadata. Now, we use metadata in order to retrieve a specific document in a database. Now, let's say in here, we have here, this is the first doc. We have here another doc here. This is the second one, okay? Now, for the second doc here, let's say we have here user1, const user1. Okay, we're going to pass here the ID. the ID of the user 1, and we have here the second user. The ID here is 2. Okay, now I'm going to take, let's say the first doc here belongs to the first user. We can take here the user ID, and then we're gonna pass it as metadata to this document, so that when we're gonna retrieve data, if we send the user ID is equal to 1, we are going to retrieve the first document. And if I take here the second user, I take the user ID, I take his ID, I pass it to the second document here, we are going to retrieve only this doc. Okay, now in order to get data, we are going to can create a function like this. Okay, fetch and passive fetch docs from passive fetch docs from vector db. Okay, something like this. We can pass here the user ID, and then we can pass here the doc ID. Okay, yeah, the doc ID, yeah, the user ID and query. Okay, like this. And that is the importance of metadata, guys. Now let me give you another example. You can see in our case here we have a parent chunk here. Okay, once we create a parent chunk, we're gonna create also an ID for the parent chunk. Now we are going to take the parent chunk. We need to create child chunks. Now once we create a child chunks for the parent chunk, we're gonna pass the ID of the parent chunk is metadata. Okay, we're gonna pass it to each chunk here. Now, when we're going to want to retrieve here the child chunk, we are going to use here this ID of the parent chunk in order to retrieve the parent chunk of that child chunk. Okay, that's how it works, guys. Okay, now let's continue. We're going to go back here, and right here you can see pass here. Let me head into the multi-vector retrieval. Now in here you can see, guys, we pass here the URLs. The URL is an array. It's going to be an array of documents. If I pass here, let's say I pass here to web link, we're going to iterate through these web links. I can pass here a web link, you can pass another one, and then we're going to iterate through, and then we're going to retrieve data. Okay, and then you can see as a web loader, you can see here pass each video. Okay, now here once we retrieve data, we're going to return it. Okay, and in here you can see we create here metadata. We pass here original URL, and we pass here meta source. We pass here only the URL, and we pass here the doc ID. Okay, now we're gonna pass another function, create parent docs. It takes the raw docs and doc ID. Now in here we create a parent chunks. You can see the chunk size is 2000 and the chunk overlap is 400. Now in here we're gonna take here this parent chunk here. We are going to create a UUID for it. Okay, you can say I pass a chunk ID, UUID, and then I'm gonna pass here the doc type is metadata parent. And I'm pass here the metadata that chunk ID, and pass that ID, and then I pass here another metadata parent ID, and pass the chunk ID, metadata source, and pass the chunk ID, and metadata doc ID, and pass here the doc ID. Now we're gonna create a function that allows us to create child chunk. You can see we pass here the parent doc and doc ID, and then we pass here recursive character splitter in order to create child chunk. Chunk size is 400 and chunk overlap 50, and then we're gonna have here an array of documents. Okay, we can take the big chunk and then we split it into small chunks, and here we're gonna have here child splits. This is an array of documents. Now I'm going to take here this small array of documents. I'm gonna iterate through, and then I'm going to get access to the parent ID here. You can see here we generate a parent ID. Now in order to get access to it, I pass here an index parent ID, okay, and then we pass here parent doc. You can see this parent doc here. Parent index, that's metadata. I get access to the metadata of the parent documents. And then here, I'm going to extract here the ID, the generated UUID here. Now I'm going to pass here metadata.doc type here, split. Split here represent the child chunk, and then is equal to the doc type here is equal to child, and then we'll pass here parent metadata.chunk ID. We pass here the doc ID here. We pass the parent doc ID to the child chunk. Okay. Now we are going to pass here the other metadata like metadata chunk ID. We pass here child, and then pass here parent metadata.chunk ID, and then I pass here metadata source, split metadata.chunk ID, and then here I'm passing the doc ID. Now we're gonna pass a function doc embedding multivector. Now the goal of this function is to create embeddings of the parent doc and embeddings of child doc. Now I'm gonna pass equal here in order to create embeddings, Pinecone, and then I'm gonna call here load docs. You can see pass here the URLs. The URLs is basically an array. Yeah, we can pass here web link that we want to extract the data. And then here we're gonna take here these raw docs. We're gonna have here raw docs. It's basically an array. And then we are going to pass it to a function, create parent chunks. We're gonna take these raw docs, we're gonna split it into multiple chunks. And once we have these big chunks, we're gonna take now this big chunk, we're gonna pass it to another function, create child chunk, in order to create small chunks of these big chunks. Now we are going to take here the parent chunk and the child chunk, we're gonna pass it to a vector database, okay? And then we're gonna pass a console.log to signal us that we just embedded, okay guys? And you just learn how to create a multi-vector embedding pipeline, guys, okay? You just learn how to do it, guys. And here the process is pretty simple. We have to take here a doc, we split it into multiple chunks in order to create parent chunks. Then we're gonna take these parent chunks in order to create small chunks. And then we're gonna create embeddings of parent chunks and small chunks and pass it to a vector database. That's how it works, guys. Pretty simple. And now I'm gonna create here another pipeline, a retrieving pipeline. Now we need to retrieve data. Now how we're gonna do it? Okay, let me explain you again how we're gonna do it, guys. Now I'm gonna go back here. You can see in here, as I said previously, let me get rid of this and remove this. We are going to the user, we have here user. Okay, we're gonna construct a query, and then we are going to pass it to an embedding model in order to create embeddings. We're gonna have here embeddings, and once we have embeddings, we're gonna use these embeddings in order to retrieve here child chunks. We're gonna have here child chunks, okay? And once we have child chunks, we're gonna use here, we're gonna retrieve here the metadata, or the metadata. We're gonna retrieve here the metadata in order to get access to the ID of the parent doc. And once we have here this ID, we're gonna use it in order to retrieve the parent chunk, the parent doc in a vector database. And then we're gonna take here this big chunk, that's what we're gonna pass to the LLM, okay, in order to have a better generation. Now, let's see how to do it. Now you can see pass here the doc ID, but also the query. Then here, I'm going to pass here the doc ID, okay, and the query. And then you can see we have a constant key parent, okay. I'm gonna use this constant here in order to retrieve top 3 documents. Then I instantiate here in order to create embeddings. Then here we're gonna pass a Pinecone, and then we are going to pass it these embeddings in order to perform similarity search inside the vector database. And then here you can see here we invoke here function similarity search. We pass it the query, and here I'm going to retrieve here top 10 documents. And you can see doc type, I'm doing filtering. I want to retrieve first child chunk. You can see doc type, we pass the child ID and pass the doc ID. And once we have here the child chunks, we're gonna use these child chunks in order to retrieve parent chunks, okay? And here I'm going to pass here vector store similarity search. We pass here the query, and then you can see here we have here parent chunks ID. We're gonna take it, and then we're gonna pass it right here. Now we're gonna get into the command prompt and we're gonna try this pipeline, okay? That's what we need to do. And guys, as you can see at the top here, once we run this pipeline, we're gonna pass it to property. Here we're gonna pass it an object. You can see the doc embedding pipeline. Take here the URLs. This is an array. As you can see right here, this is an array, but also it takes here string, the doc ID that we're gonna use in order to retrieve the data. Now I'm gonna pass here the doc embedding multi-vector pipeline. We pass here the URL that we want to embed. We're gonna extract data and then we're gonna embed it. And I'm passing the doc ID. Ben123. Okay, we're gonna use here this doc ID in order to retrieve again the data. You know, the data is gonna be stored by metadata. Now, in order to get that specific metadata, we're going to use here the doc ID. Now let me try to run this and see what we're gonna get in here. And pass here this is the name of the pipeline. Let me see here, we're gonna run here this multi-vector retriever, and here in order to run it, I'm gonna head into in here and I'm pass here node source / multi-vector retriever.js, and then I'm tap enter, and then we're gonna embed this. Okay, you can see loading raw docs. Okay, they load the documents, and you can see actually they split it into big chunks and small chunks. Okay, and here we're gonna take here these big chunks and small chunks. We are going to pass it into the vector database. Okay, you can see in here we have this big chunk and we have small chunks. Okay, now as we just pass all of this data in the vector database, now we're gonna retrieve it using a retrieving pipeline. Now in our case, we're gonna use here this retrieving pipeline in here query multi-vector. Okay, I'm gonna use here this retrieving pipeline in order to feed data. Now I'm gonna copy that and I'm pass it in here. Okay, I'm gonna comment now. We're gonna comment the doc embedding pipeline, and now we're gonna pass here cons results, and here I'm pass here away. We're going to pass here query multi-vector, and the query multi-vector here takes to an object. We're gonna pass here the doc ID and pass the doc ID like this. Doc ID is Ben123 like this, and we're gonna pass here the query. And for the query, guys, we're gonna head into this file right here, and I'm going to take here the query. Let me head into the retrieving pipeline, and I think we got here the query. Okay, let me check here. I can try to take this and then I'm pass it right here. Tabs, yeah, I'm gonna cut this, and then we can go ahead and head into the multi-vector retriever. We can pass it in here like this. Okay, like this, and now I'm passing cons. Yeah, I'm gonna pass here console that results, and we're gonna get here an object. Okay, you can see if I click here, the query multi-vector function returns here an object. We're gonna have here parent doc. Okay, now let's try to run this and see what we're gonna get here. I'm pass here now. We're gonna pass here. Yeah, we're gonna pass here the same command. Okay, multi-vector, and we're gonna retrieve data now. And yeah, you can see actually you have data here, guys. You can see the in operator. The in operator must be followed by a list of strings or a list of numbers. We got this. We are passing here now. You can see actually this array, it is here now. It contains now. I'm trying to pass it. I'm passing here. You can see we have here now. That's why we don't get data. Now I'm gonna get rid of not there. We need to pass only string. Now, in order to pass string, I'm going to pass this filter. I'm going to take here the parent chunks ID, filter, RM. I'm going to check if we have undefined or now. I'm going to remove them. Now, I'm going to take here the filtered chunks ID. I'm copy this and pass it in here like this. Now, let's try to retrieve again data here. I'm going to try to retrieve data. We're going to run this and see what we're going to get here, guys. Yeah, you can see actually we are retrieving data. We are retrieving data. And you can see we have here the parent docs. This is an array of documents. Okay, and yeah, you can see we have here prompt engineering, and we have here types of prompt engineering. Okay, you can see actually we got data in here. You can see we have here the data. Now what I'm going to do, I'm going to get rid of this document right here. You can see we have here an array of documents. Now I want a string so that we can pass it to the LLM, and then the LLM can analyze it. Now I'm going to pass here. I'm going to take here a gather function right here for my document string. We're going to take here an array of documents. We're going to convert it into a string. I'm passing here, and see I'm passing here const doc to string. We're going to pass the doc to string. Okay, is equal to format doc a string. We're going to pass here this array of documents. I'm going to cut that. We're going to pass here that parent docs, something like this. And we're going to take here now, we're going to pass this here, and then we're going to see what we're going to get here, guys. I'm going to run this again, and then you're going to see we're going to get data here. And you can see, guys, that actually we got data here. You can see we have data, and you can see we have here 0 shots, few shots, and we have here instruction prompting, self-consistency, chain of thoughts. Okay, this is the data. This is the retrieved data. But actually, this retrieved data contain noise. We have noise. We have irrelevant data inside of the data. You can see we have here symbols. Let's say we want to pass this data to the LLM in order to generate the context. Maybe sometimes the LLM can generate this. You can see we have symbols. Okay, this is noise in the data. Now we need to get rid of this noise. We're gonna use here another technique here. Let me move here. We are going to use here contextual compression retriever in order to get rid of noise in the data. You can see this data contains symbols. You can see we don't need symbols, okay? And also you can see we have the date. We don't need that. We're gonna get rid of this irrelevant data, okay? Now we're gonna use here contextual compression retriever. Now you can see we follow the same process. We're gonna retrieve here again child chunks. And then we're going to use here child chunks in order to retrieve parent chunks. And once we have here these parent chunks, we're going to take it and then we're going to pass it to a compression layer. So what the compression layer basically does, it removes noise from the data. That is the goal of a compression layer. It allows to remove noise from the data, okay? Nothing else. Now we're going to pass here a compression layer. I'm going to head in here, guys. Okay, you can see in here we have here this line. I'm going to comment this, and then I'm passing this code here that allows us to add a compression layer. Okay, and in here, in order to add a compression layer, you're gonna install a package. Okay, you can see I pass here LangChain extractor. Okay, I import it from LangChain class. You can see I pass here LangChain extractor. A LangChain classic /retrievers /document compressor /chain extract. And now in order to get this function right here and to get the contextual compression retriever function from LangChain classic, you're gonna head on npm.com and type here LangChain /classic. Type these commands. And you can see this package contains functionality from LangChain v1 that has been moved out of the main LangChain version. Okay, now install this, and then you're gonna get the contextual compression retriever, but also you're gonna get here this function. Okay, now in order to add this layer, we're gonna pass here LangChain extractor that from LLM. We're gonna pass here the LLM, pass here Supabase, and here I pass here another function, contextual compression retriever, and then pass here base retriever. We pass here the compressor. The compressor is the LLM because we're gonna take data, we're gonna pass it to the LLM, and then the LLM is gonna extract relevant data and remove noise. And then pass here vector store. Here we have here the vector store. We're gonna take the vector store, and then we're gonna pass here as a retriever. And I'm gonna retrieve here top 10 documents, doc type, parent. Doc type, we're gonna pass here parent. Now we're gonna take here the filtered chunks ID, and that's what we're gonna pass in here, like this. And I'm gonna take now this. I'm going to pass here now, okay? Retrieve docs, something like this. And here, if I pass here now, retrieve docs, you're gonna see we're gonna get data that doesn't contain irrelevant data. Now let's see again here. I'm gonna run this and see what we're gonna get here, guys. Actually, we are retrieving data, and yeah, guys, you can see that actually we got data here. You can see we have your types of prompt engineering, and at the bottom here you can see we have noise again in the data. You can see we have here symbols. Okay, we have here symbols, guys. Now how to get rid of these symbols? Now to get rid of these symbols, what I'm going to do, I'm going to improve the prompt. Now you can see I'm going to show you something. You can see I head into Node.js, okay? And then you can see at the top here, we are using here package, LangChain classic. And then what I'm going to do in order to get rid of these symbols, I'm going to look for the package LangChain. You can see here's LangChain. Now we got here classic. You can see we have here classic. And then I'm going to head into this folder. You can see here's this folder. I'm gonna scroll a little bit. You can see we have here retrievers. I follow this path right here, LangChain /classic /retrievers, and then you can see in here /document compressor. Okay, you can see I pass here the path, and here you can see we have here the prompts. Okay, we have here the prompts that we use in order to extract relevant data. So actually this prompt doesn't work pretty well. Okay, I'm gonna improve it. Okay, I got another prompt right here that I've used ChatGPT in order to improve this prompt. Okay, I'm gonna take this and then I'm going to pass it there. Okay, I'm passing this prompt. Okay, this prompt is pretty strong than this one. Okay, than the previous one. I'm gonna head into here and then I'm gonna pass you this prompt. Okay, and it's gonna work. You can see here it looks like the previous one was like this. Given the following question and context, extract any part of the context as it is that is relevant to the user question. If none of the context is relevant, return no output. Okay, and here you can see I pass you remember, do not edit the extracted parts of the context. Question, pass it the question, and here pass the context. This is the previous query that comes along with this package. Now I'm gonna get rid of this and I'll pass prompt. Okay, this one is pretty robust. Okay, it's pretty robust. Now if I run this, we aren't gonna get here irrelevant data. Now I'm gonna run this again, and then you're gonna see here we're gonna get data here. Let's wait a bit. You're gonna see we're gonna get here data. Yeah, you can see actually the LLM extract only relevant data. Okay, it cannot return here symbols. Okay, and this is the context that we're gonna pass to the LLM in order to generate the response. Okay, you can see I just modified the system prompts that was in here. Okay, you can try to copy it. You can try to copy it, guys. Okay, and here if you want to modify it too, when you're gonna install the LangChain Classic package, in order to modify it, you're gonna head into LangChain, you're gonna head into this here, and then you're gonna head into retrievers, document compressors. You're gonna see here, you're gonna have here chain extract prompt.js. Okay, you're gonna modify the system prompt that you're gonna see in here. Okay, let's go back now, and if we run this, we're gonna get rid of noise. Okay, that's great. Okay, now I'm gonna close this, and at the bottom here we can pass another query. You can see we have here some user query. If I run this, let me try to run this. Types of prompt engineering. I'm going to pass here this one here, and then let's see what we're gonna get here. I'm pass this, and I'm gonna run this too. We're gonna see what we're gonna get here. Let's wait a bit. Actually, we are retrieving the data, and once we retrieve data, we're gonna pass it to the LLM in order to remove noise in the data. Again, we got here this. Let me pass here again another input here. Let me pass here now this prompt engineering approaches and the application. I can take this and then I'm pass this one right here. Let's see again what we're gonna get here. Okay, let's see again what we're gonna get here. Let's wait a bit. Okay, you can see actually the LLM returns only relevant data. Okay, you can see that's cool. This is how we can use contextual compression retriever in order to remove noise in the data. Okay, you just learn how to use it. Okay, this technique right here is pretty a good technique. Okay, contextual compression retriever. Okay, this is how we use it. Okay, we mix a parent document retriever plus by adding a compression layer, a layer that allows to remove irrelevant data. Okay, that's it, guys, for this chapter. Now I'm going to show you how to use now this pipeline. We're going to learn how to use here this multi-vector pipeline inside the retrieving pipeline. Yeah, I'm going to pass it inside the retrieving pipeline. You can see in here, guys, we have two prompts here. We have a prompt that allows us to generate multiple versions of the user inputs, and we have another prompt that allows the LLM to generate the response based on the retrieved data. Now, what I'm going to do, you can see in here, if I scroll at the bottom, you can see in here we have this, and you can see in here inside the for loop here we use here query vector DB. This is naive retriever. In here we use a simple retrieving technique in order to retrieve the data. Now I'm gonna replace it with this one right here. We're gonna head into multi-vector retriever, and then I'm going to copy now this. Okay, I'm gonna take this and then we're gonna use it there. I'm going to export it. Let me see it right here. Okay, query multi-vector. Okay, stuff like this. We're gonna cut this, and then we're gonna pass it in here. Okay, we're gonna head into retrieving pipeline, and then I'm gonna pass it in here. Okay, I'm gonna pass it here like this, and here what we have here the doc ID. And pass here the doc ID here is Ben123, and the doc ID is a metadata that we're gonna use in order to feed data. And here we're gonna pass here for the query, we're gonna pass here the question like this. And once we have here retrieve documents, we're gonna push it inside the retrieve doc array. And now let me import here this. I'm gonna import it and pass here imports and pass here from, we're gonna pass here that multi-vector retriever.js and pass something like this. Okay, and if we move at the bottom here, and I'm gonna remove this. We are going to take the retrieve data, and then we're gonna pass it to the LLM. Okay, and here you should pass here something like this. We're going to pass here results that retrieved doc. Okay, you can see if we head into the query multi-vector function, you can see in here the bottom, I'm returning here an object. Okay, and the retrieve docs is an array. Okay, now I take it, and then we're gonna push it into this array. Now we're gonna run this and see what we're gonna get back here. Okay, I'm gonna run this, and here you're gonna see we're gonna get here the data. You can see this the first. Okay, we retrieve the data in the database. What are the different types of prompt engineering techniques? And again, they're gonna retrieve data, types of prompt engineering methods, prompt engineering approaches, and the applications. Okay, yeah, you can see now we have here a generated response. Okay, based on the provided context, the types of prompt engineering, we have here zero shots, few shots, and we have here instruction prompting, self-consistency, channel thoughts, and pass here automatic prompt design. And here we have here number 7, basic prompting. Yeah, you can see for the number 7, it isn't a prompt engineering technique. Okay, now let me pass here what is channel thoughts as question. Okay, we're gonna see what we're gonna get here. And as the user input, I'm gonna move at the top here, and here let me see here the query. Okay, we're gonna move at the top here. Yeah, you can see it's the input and pass here what is channel thoughts. What is channel thoughts? And we're gonna run this. Let me see what we're gonna get here. And once we run this, define channel thoughts. Okay, explain the concepts of channel thoughts in AI. What is the channel thoughts approach in natural language processing? Okay, now let's see here. Okay, channel thought is a prompting method that encourages a model to generate reasoning chains before producing the answer. It involves explicitly asking the model to think step by step, often using phrases such as "let's think step by step" and "let's work this out step by step to be sure we have the right answer." Okay, this is the right response. Okay, channel thought is a prompt engineering techniques where we tell the LLM to think step by step. Yeah, this is the right answer. Okay, and guys, this is how you can use multi-vector retriever in order to improve the generation. Okay, now we're gonna talk about metadata filtering. Now I'm going to head into in here. We're gonna pass here another file, and I'll name it metadata filtering. Metadata filtering. .js, something like this. And we're going to use here metadata in order to retrieve a specific doc in the vector database. You know, in the vector database, we can put in a lot of stuff. Let's say we can put in docx. Docx contains y things. We can put in docw, and docw contains something. Okay, what if I want to retrieve only the docx? Now I'm gonna use metadata. Okay, in order to retrieve only the specific documents, and we already use metadata, guys. If you notice, I want to carve this in order to remove confusion, guys. In order to make you understand everything, you know, in the multi-vector retriever.js, we use here metadata. You can see when I pass here the doc ID, you can see in here when we are trying to fetch data, we pass here doc ID. Doc ID is metadata. Now I want you to understand pretty well. That's why I create the chapter 7, okay? We're going to talk about metadata. I'm going to head into now inside the embedding pipeline. I'm going to copy everything here. We're going to put it inside the metadata right here, okay? And what I'm going to do in here, guys, you can see at the top here, we have here document loader, okay? And yeah, this is the document loader. And then we use it in order to retrieve the data, okay? Now I'm going to come here, the document loader, and then here I'm going to pass here an array of document. I'm passing new document, and then I'm pass here the page content. I'm pass here Ben is a programmer, okay? And I'm gonna pass here now metadata for Ben, metadata, and then I'm pass here user ID, like this. I'm pass here, and we're gonna pass here, and pass here Ben 123. We're going to pass here another user. I'm gonna copy this, okay? We're gonna pass here another doc here. We're gonna pass something like this. Ben is a programmer. And pass here John is a driver, okay? Something like this, driver. And here for the metadata for John, we're gonna pass here John 123, something like this. Now this is the data that we're going to pass inside the vector database, and then we're going to use metadata in order to retrieve a specific document, okay? Now what I'm going to do, I'm going to get rid of this here, and then we're going to run this, and after that we're going to try to retrieve data, okay? I'm going to take that, and I'm going to get rid of this string here. I'm going to remove this, okay? And now I'm going to head into the console here. We're going to run here the file. I'm passing node source, and then I'm passing /metadata dash, I'm passing filtering the JS. Then I'm tap enter. You're going to see we're going to have your data, okay? Yeah, we are going to embed data. Okay, yeah, you can see finish embedding doc. Now I'm going to head into the retrieving pipeline. We're going to copy something. Yeah, query vector DB, we got a function here. Okay, embedding pipeline here. Okay, I'm going to copy a function. Okay, let me check here. We have here this is the multi-vector retriever. I'm gonna head into the retrieving pipeline, and I'm going to copy something. Okay, yeah, you can see in here we have the retrieving pipeline. I'm going to take that, and then I'm gonna put it inside the metadata file. I'm gonna pass it in here, okay? I'm gonna comment this. We aren't gonna run this, okay? Like this. And now we're going to invoke this and pass here this and pass here const query. Yeah, and pass here result. Yeah, its result is equal to away. We wanna pass here query vector DB, okay? And we are going to pass here the query. And you can see the similarity search here function takes here a string is parameter, but also it takes here a filter. A filter is an object, okay? Now I'm going to pass here filter and pass here filter, okay, filter like this, and then I'm going to pass here the user ID. Let's say I want to retrieve here Ben 123, something like this, and then if I pass the query Ben, let's see what we're gonna get here. Okay, console.log and pass here result, something like this. Okay, now we're gonna run this file again. Let's see what we're gonna get here, guys. Okay, yeah, actually we have another filter is not defined, okay? As filter is not defined, I'm passing an object, okay? You can see it takes here the query, the number of doc that we want to retrieve. Here I pass here 10, and here I'm passing the filter. We're gonna run this again and see what we're gonna get here, guys. Yeah, you can see actually we have here one doc, okay? We got here one doc. Ben is a programmer, and you can see here's the metadata. So what if I pass here Ben, I pass here something like this? Let's see if we're gonna get data. We aren't gonna get data. Yeah, let me pass here first Ben. Okay, I'm passing Ben, and then for the metadata, let me pass here by an invalid metadata. I'm passing here this as metadata. We aren't gonna get data here, guys. I'm gonna run this. Okay, let's wait a bit. Yeah, you can see actually we have here an empty array. We don't get data here. And yeah, you can see I pass this. What if I pass here an invalid keyword? Let's see. The metadata is valid, But we are going to try to look here to try to see if we're gonna get here this input right here. Now, if I run this, let's see what we're gonna get here. I'm gonna run this, and then let's see right here what we're gonna get. Yeah, you can see actually we got data. We got data, guys. We got data. Yeah, we got data because we pass here a value metadata. Now, if I want to retrieve a John data, you can see for John here, this is the metadata. We can use now this. If we want to retrieve John data, we can use here this specific metadata. You know, let's say here, you know, we can have here this doc. Okay, I can copy, let's say, this doc of John right here. And here, let's say we pass here a biography of John. Okay, John biography. Okay, biography. Yeah, I'm passing John by. We have here a biography of John. Now, if we try to retrieve data, we're gonna get here John with his biography. Okay, now I'm going to pass here now this metadata. I'm gonna take that and we're gonna pass in here. Okay, something like this. And I'm passing J, and we are going to get data. Let's run this. Let's see what we're gonna get here, guys. Yeah, you can see actually we have here one doc. John is a driver. Okay, we have here one doc here. Okay, John, yeah, we have here one doc based on the user inputs. So let's say I pass here this, and then I pass here this, something like this. We're gonna have here two doc. Okay, yeah, John bow, yeah, something like this. Let's see if we're gonna get data again here. We're gonna get here two doc here. Yeah, we can't get two doc, guys, because I didn't run this function. Okay, we need to embed that. Okay, first of all, we need to embed that. Now, let me first do this. Okay, we're gonna embed that doc2, and once we embed it, we're going to retrieve data again. Okay, yeah, we finish embedding data. Now I'm gonna uncomment this, and we're going to retrieve now data. We're gonna comment this. Let's retrieve the data again here. We're gonna run this. Yeah, you can see actually we have here John bow. John is driver. John is driver. Yeah, we have here data. Okay, you can see we have here data, and that's how we can use metadata in order to select a specific record, a specific document in a vector database. Okay, you understand how metadata works. Okay, no confusion, guys. Now you can come back here if you have confusion. Now you're gonna understand the why of metadata. You can see we use here metadata in order to retrieve a specific doc. Okay, now you understand everything about metadata. I see you in the next one. Alright guys, welcome to the second lab. We're going to talk about types of RAG architectures. For this lab, we're going to give 30% of theories and 70% of practice. We need to mix everything, theory and practice, so that we can understand everything pretty well. So before we get going, I need you to have the basics of LangChain, like you know how to create a multi-agent system. If you don't know how to do that, I got a full course about LangChain. I teach how to build a multi-agent system. Go check it out, guys. Now let's start with chapter 1. We're gonna talk about naive RAG. Okay, naive RAG is the simplest version of RAG. Now you can see here, guys, we have here this little diagram. Now, this is a naive RAG, okay? In here, we don't have a complex stuff. Everything is simple in here. You can see the first thing we have to do in a RAG system, we have to upload documents in a RAG system. We're going to take here these documents. We're going to pass it to the embedding model. We're going to convert it into embeddings. And once we convert these docs into embeddings, we're going to take here these embeddings. We're going to pass it to a vector database. Now, for the second step here, the user now can craft a query and then forwards it to our system. We're going to take that query, going to convert it into embeddings, and then we're going to use here these embeddings in order to perform similarity search in a vector database so that we can get data. Now, this is naive RAG. Okay, you can see everything is pretty simple here. Okay. Now you can see right here we have some components of naive RAG architecture. We have here document chunking, document embedding, vector database, retriever, and we have the LLM for response generation. Okay, these are some components of Naive RAG system. But this kind of system has some cons like scalability issues, context limitation, limited processing. We don't have to do a lot of job in background. Okay, these are kind of problems that we have with Naive RAG. But it works sometimes. But for complex documents, it may not work. Okay, now in order to work with complex documents, or if you want to do advanced stuff, we are going to explore some advanced RAG techniques. Now we're going to start with Agentic RAG. So what is Agentic RAG? Agentic RAG is a type of RAG architecture where we use AI agents in order to retrieve data in a vector database. So what is an AI agent? An AI agent is an LLM with tools, okay? A tool allows an LLM to take an action, okay? Let me draw here a little architecture, a little diagram, okay? You can see we have here the agents. The agents can have a tool that allows it to retrieve data in a vector database. It can have a tool here that allows it to, let's say, to create multiple versions of the user inputs. This is an AI agent. An AI agent is an LLM with tools. Now, once we pass an LLM tools, it can take action. Maybe it can go on the internet looking for data. It can retrieve data in a vector database. That's how an AI agent works, okay? We can use here a group of AI agents that collaborate together in order to fetch data in a vector database, okay? Now you can see in here, let's say we can build a SaaS system, okay? You can see we have the manage agents. Now, once the user forwards an input to our system, we are going to pass it to the manage agents. Now, the manage agents, it's going to forward that input to the planner agents. Hey, planner agents, I need you to make a plan in order to satisfy the user based on these inputs. Then the planner agent is going to create a plan immediately. And then once you finish creating the plan, it's going to forward it back to the manage agents. Now, once the manage agent has the plan, it's going to read the plan here, and then it's going to forward here this plan to the retriever agent. Hey, retriever agents, generate multiple versions of the user inputs based on this plan, okay? Then the retriever agent is going to act again, and then it's going to return the response back to the manage agents. Then the manage agent is going to proceed with the retriever agent here. This is another A agent. And then here you can see the retriever agent has here a tool that allows it to retrieve data in a vector database, okay? Then the retriever agent can interact with external tools like Pinecone in order to get data. And once it gets data, it's going to return it to the manage agent. And then the manage agent is going to forward the data to the user. That's how an agentic RAG system works, okay? It's pretty simple, guys. That's how it works, okay? Now I'm going to show you how to implement an agentic RAG using AI agents, okay? That's what we're going to do right now. Now I'm going to show you how to build it, and later, guys, if you want to learn advanced stuff, you're gonna check here these two videos, okay? To learn about multi agents and context flooding, I talked about streaming a message. You're gonna learn how to build multi-agent system that allows you to chat over main documents. You're gonna learn how to build memory agents. And I talked about MapReduce techniques for generating reports over 200 plus pages documents, okay? You can check out these two videos. They're going to help you, okay? For projects, you're going to check this video. Now, before I show you how to build this multi-agent system using LangChain, we're going to take a look to this agentic RAG call loop. Now, you can see here we have the user. The user crafts an input, forwards it to the LLM. The LLM is going to analyze it, and then it's going to decide if it can use a tool here. It can call a tool in order to feed data. Or if it doesn't call a tool, the LLM can respond immediately. Okay, this is how it works. So if you call a tool, the tools can return here the response to the LLM, and then the LLM can generate the response to the user. This is how it works, guys. We have here the user. The user forwards an input to the LLM here. Then the LLM is going to analyze it. Do I need to call a tool? If yes, the LLM is going to call a tool here. And then the tool, if the LLM call a tool, the tool here, it's going to return here the response. Then the tool is going to return the response here to the LLM. The LLM is going to analyze it, and then it's going to generate here the response to the user. If the LLM doesn't call a tool, we have here another alternative. It doesn't call a tool, the LLM can generate the final answer. If the user passes an input like hello, the LLM is going to respond immediately. Okay, this is how an agentic RAG call loop works. Okay, it's pretty simple, guys. Now we're going to head into the practice. Now you can see here, guys, you can see I've already passed here folder RAG full course. Okay, here you need to have the basics of LangChain. You need to know how to create a multi-agent system. Okay, these are the basics. Now in here, guys, you can see we have here the manager agent. Now the manager agent here, let me start here with the manager agent. You can see here's the manager agent, and the manager agent here has a prompt, a system prompt. UI chat PDF, a manager agent responsible for answering user questions about documents using a coordinated multi-agent system. You also support natural casual conversation when the user's message does not require document retrieval or factual verification. If the user passes something like hello, how are you doing, the LLM can react immediately. It doesn't need to create a tool for this kind of message. And here we pass here primary responsibility of the LLM. And here, guys, pass here the agents. I inform the main agents that it is a planar agent, it is a multi-query agent, and it is a retrieval agent. When you are building a multi-agent system, you have to inform the main agent about its sub-agents so that it can know how to call them. Now, here's the system prompt. It's pretty huge, guys. And then I pass here a basic React agent. We're going to pass here the LLM. We're going to pass here the LLM here. And we're going to pass here the LLM, the system prompt, and here we pass sub-agent as tools. You can say pass here the retrieval agent as a tool, a multi-query agent is tool, and a planar agent is tool. Now here's the main agent. You can see I follow this diagram right here. Now we're gonna move to the retrieval agents. I'm gonna head into sub-agents, and you can see here's the retrieval agent. Now this is the prompt for the retrieval agent. We pass it in here, and we pass here a tool to the retrieval agent. You can see on this diagram, the retrieval agent here has a tool. For this one here, this is a model, okay? This is a tool. We're gonna pass here to a retrieval tool that allows the agent to feed data in a vector database. That's what we're gonna pass there. And you can see here, you can see, let me show you something. You can see as we pass here retrieval tool, if I head into in here, if we head into tools folder, you can see, guys, we have here this is a tool, and we pass here the query multi-vector function in order to feed data in a vector database. I've already explained you how to create this function. Okay, previously we talked about parent document retrieval, contextual compression retrieval. We talked about that. Now I pass here the retriever, and once the LLM invokes the tool, it's going to return data. Okay, and once the retrieval agent has here data, it's going to take the data and then it's going to pass it back to the manager agents. Now we are going to move to the multi-query agents. The role of the multi-query agent is to generate multiple versions of the user input and nothing else. And here you can see we pass here the system prompt. You are the multi-query agent. Your job is to generate multiple high-quality set queries from the user's original question using step-back prompting. We pass here some rules, and we tell it to generate free versions of the user inputs. And we pass here now the model. We're going to pass the model, the system prompt, and then the multi-query agent is going to return multiple versions of the user input to the manager agents. Okay, we're going to return that data here. And now we have here the planar agents. For the planar agents, the goal of the planar agent is to create a plan. How are we going to feed data in a vector database? Which process are we going to follow? This is the only goal of the planar agents. Now you can see here's the planar agents, and we have here the system prompt. You are the planar agent. Your responsibility is to analyze the user's request and produce a structured execution plan. You do not answer the user directly. Your output must include the user intent, require information sources, a step-by-step plan for the managed agent, whether multi-query retrieval is needed. Yeah, this is the plan. And to pass here, you're gonna pass it the LLM and the system prompt. And then we have here the planner agents. Okay. Now you can see if we head into the manage agents, we take here the retriever agents, the multi-query agents, and the planner agent. We pass it as a tool to the main agent because the main agent is gonna call these two. You know, as I said before, an AI agent is an LLM with tools. Once the LLM has this tool, it's gonna call this tool right here. Once we pass an input, it's gonna read the system prompt, and then it's gonna start immediately with the planner agents. Now let's get into the code and try this. And here's what I'm going to do. I'm gonna pass here this middleware, tool monitoring middleware, in order to see which, if we're gonna try to pass this here in order to check if the agent is gonna call the retrieving tool, okay? And I'm going to pass here now this middleware, and we're gonna pass here this. If you don't know what is a middleware, go check out the LangChain course, okay? I teach everything you need to know about middleware, okay? And now I'm gonna copy you to something. I'm gonna copy something. Okay, I'm going to copy this, and then I'm going to head into the agentic folder, and then pass here another folder LLM. We're gonna pass here LLM.js, something like this, and then I want to pass this in here. Okay, you can see in here for the model pass here queen, and if we head into the manage agents, you can see I pass here the LLM.js file, and if we head into the sub agent retriever, you can see I pass in here too. But for this ID here, I'm gonna get rid of this. We aren't gonna use this. I'm going to remove here this ID. Okay, let me get rid of this here. Okay, something like this. Okay, that's cool. Now we're gonna head into the command prompt and we're gonna run this and see what we're gonna get here, guys. Okay, I'm gonna run this, and you can see in here, if we head into the manage agents, you can see I pass here what is prompt engineering. Let's try to see if the manage agent is gonna call a retrieving tool. Yeah, guys, you can see actually the manager agents call here the planner agents. Then here the manager agents call the multi-query agents or the multi-query agent to generate multiple versions of the user inputs. Then here it calls the retriever 3 times. You can see retriever, retriever, retriever. They call the retriever 3 times in order to retrieve data. You know, the multi-query agent generate here 3 multiple versions of the user inputs. That's why they call here the retriever agent 3 times. And here, if we scroll at the bottom here, you're gonna see we have here the data. You can see here is the thinking of the AI. And then here we have the overview of prompt engineering. You can see his data. And if I cap this, and I'm going to head into in the file, and then I'm pass it the data right here. Okay, you can see prompt engineering involves designing and refining inputs, okay, to optimize a model outputs. And here you can see, I don't see here the definition of prompt engineering. We don't see it. You can see in here, we got here an overview. Yeah, this is the right answer, okay? Because in here you can see pass here what is prompt engineering. That's why we got this definition. If we pass a question like types of prompt engineering, the LLM is gonna return here types of prompt engineering. Okay, you can see it's cool, guys. And in order to learn advanced stuff, I invite you to go check out these 2 videos, guys. Okay, in order to improve your level. Now we're going to talk about adaptive RAG. So what is adaptive RAG? Adaptive RAG is RAG techniques where we create a node that allows to route the user input to the most effective system. Now let me explain clearly. You can see here, guys, we have our system in here. Okay, let me go to this diagram first. You can see in here, this is a RAG system. Now we're gonna create here a node that allows to analyze the user inputs. Let's say the user pass here hello. If the user pass hello, the LLM can respond immediately. How can I help you today? So if the user pass, what is the capital of France? Now the LLM is gonna say the capital of France is Paris. So what if we pass here again? What are trending now in AI? if I pass this kind of question to our system is gonna fail to respond to this kind of question because the LLM is not connected to the internet. Okay, it's gonna fail. Now we are going to use here the manage agent as a writer. Okay, let's say if the user passed this kind of question here, the LLM is pretty smart to determine if it can call here the planar agents or it can call here the multi-query agents. Okay, and if we pass here this kind of question, what are trending now in AI, the manage agent can decide to call a tool here. You can see I just passed here a website tool. You can see if we had a look to our previous diagram here, you can see the manage agent doesn't have a tool. Now if we pass this kind of question here, what are trending now to the actual system that we have in here, the manage agent is gonna fail. It's gonna tell us doesn't have access to the internet. So what if we pass it a set2? Now once we pass here a question to the system, the manager agent is gonna analyze the question, and then it's gonna decide if it's gonna call the planar agent, the multi-query agent, or the retrieval agent. It's gonna think a little bit, and once it finish thinking, it can decide if it can call a website tool or it can call a planar agent or a multi-query agent. Okay, that's how it works. And here you can see with multi-agent system, it's pretty easy to implement adaptive RAG. The LLM is pretty smart. It's gonna analyze. Okay, we're gonna use here the manage agents. It's pretty smart. We don't have to do anything else because once we pass it the inputs, it's gonna analyze it. The manage agent is the query analysis node. Okay, it's gonna play the role, and once it determines, these kind of questions needs to be processed to our knowledge base system, it's gonna forward the input to the planar agents, and then after the planar agent finish creating a plane, it's gonna forward the input to multi-query and then to the retrieval agents, and then they're gonna pass data to the manage agents. If the manager agents notice that this kind of question needs a tool, let's say a website, it's gonna call this. Okay, and that's how adaptive RAG works. Okay guys, you can see adaptive RAG is a RAG techniques, which is pretty easy. It's a technique that allows to determine the most effective system that can answer the user input. Okay, that's how adaptive RAG works. Now we are going to add here set2. If we pass this kind of question to our system, it's gonna fail. It's gonna fail. Now I'm going to add a set2 to our system, and then if we pass you this kind of question, the LLM is going to analyze the input, and then it's going to determine which is the best tool to call. Okay, you can see it's pretty easy. Now let's head into the code and add a set2 to our system. And now what I'm going to do in here, guys, I'm going to add here something to the system prompt. I'm going to pass here this. You have access to the following documents in the knowledge base system. I pass here the name of the book, Prompt Engineering Book. If a question is not related to the document within our knowledge base system, you can use the set web tool. And you can see at the bottom here, I pass here tools. Set tools. Use this tool when it's needed to find real-time data on the internet. Okay. If you add a specific tool to the manager agent or to a given agent, you have to inform it that it is the tool. If you don't inform an agent that it is a specific tool, it's not gonna call it. It's not gonna call it, guys. You have to inform it. Now I'm going to go in here. You can see we have a tools folder, and then I'm going to pass here another tool, set tool, and here I'm gonna use ExaSearch to make a website. If you don't have here the API key of ExaSearch, head on exa.com. You can type here ExaSearch. Let me show you how to get the API key. And here I'm pass here. Let me type here ExaSearch. I'm gonna pass the ExaSearch. Okay, and I'm tap here. It's free, guys. Head on ExaSearch and create an account. Once you create an account, you're gonna head into API key, and then you're gonna grab your API key. You're gonna pass it inside the data file. Okay, great. Now in here, I'm going to head into now the manage agents, and I'm pass here an input. What are trending now in AI, and we're gonna see if it's gonna call that tool. And I'm pass here nodes. And you can see, guys, that actually the main agent call a set2. Okay, call a set2. Now you're gonna see we're gonna get data here. You can see actually we got data here. We have a lot of stuff here, guys. You can see we have a lot of stuff in here. Now I'm going to modify here the input and pass here what is chain of thought. And pass here what is chain of thought. And pass chain of thought prompting. Okay. And now let's see what we're gonna get in here. Pass this as input, and now I'm gonna run this again. We're gonna see if the agent's gonna call the planar agent in order to create a plane. And once the planar agent finish creating a plane, it's gonna return the plane to the manager agent. Then the manager agent is gonna pass. It's gonna order here the multi-query agent to generate multiple versions of the user inputs. And you can see here it calls here the planar agents. But actually it doesn't call other agent like multi-query and retrieval agent. Doesn't call these agents. I think because the LLM knows everything about prompt engineering. You know, LLM trains on a huge amount of data. I think that's why it knows everything about that. Now let me try to pass here our inputs. And also at the end here, if you try to analyze here this, you're gonna see we have here the response to the user input. Okay. The LLM knows everything about chain of thought. You can see in here, a pass here prompting is a prompt engineering techniques where LLM are instructed to generate immediate reasoning steps. You can see it succeed. Okay, it succeed because it knows everything about the input. If you pass something it doesn't know, the LLM can try to call an external. Let's say it can try to call the retriever. Okay, I'm passing something like this. Yeah, you have access to the following documents in the knowledge base system. I'm passing a Maxi book. Talks about Maxi, which is an e-commerce website. Okay, something like this. Now, if I pass here, what are service offered by Maxi? What are service offered by Maxi? Let's see. Now, let's see which tool the manager agent is gonna call. I'm gonna run this again. Okay, let's see here. Let's see here, guys. Let's see. Okay, yeah, you can actually call the planar agents, multi-query agents, then the retrieval agents. And actually, guys, I don't have data about this book right here about Maxi. I don't have data for this book. Okay, you can see the manager agent is pretty smart. It knows how to categorize an input. Okay. This is how you can use adaptive RAG, guys, in order to route the user input to a system that allows to respond to it. Okay, you can see that all, guys. And here guys, we finish. And I'd like to tell you, when you are building a RAG system with multi-agent system, you have to write a robust system prompt. If you don't do that, your system is gonna fail. Okay, it's better to write a good system prompt. I see you in the next one. Alright guys, now I'm going to talk about adaptive RAG with self-reflection. So previously we talked about adaptive RAG. We said adaptive RAG is a type of RAG where we route the user input to a system that can efficiently answer the user question. Okay. Now we're going to add here a feature to adaptive RAG that we call self-reflection. So what is self-reflection? Self-reflection is when the LLM revises its own output. The LLM reflects on its own outputs. Let me be clear here, guys. You can see we have here the LLM. The LLM generates here the output. Okay, we have here the output. Now, instead of forwarding the output directly to the user, the LLM is gonna revise here this generator data. It's gonna say, does this data respond to the user input? Okay, if yes, the LLM is gonna forward it to the user. If no, the LLM is gonna generate again the data. That's how it works. Now, in order to understand this pretty better, we're gonna take a look to this diagram. Now you can see we have here a query analysis system. This node here, we can think of this as the manager agents. Now here the user input arrive here to the manage agents. The manage agent is going to think about it and then classifies it. If the user input is some kind of water training now in tech, the LLM is going to analyze it and then it's going to say, yeah, this kind of input is related to the web. Now let me call here the set tool. It's going to call the set tool and grab data on the internet. So if the user input is not related to, let's say, to the web, the LLM now it's gonna forward it to our RAG system. Okay. Now in here we have different nodes that we're gonna jump through in order to generate the response to the user. Okay, we have here quite a few steps here. Now you can see in here, guys, we have the retriever node. The retriever node, you can think of the retriever agents. Now here we're gonna forward the input here. The retriever agent is gonna retrieve data in the vector database, and then it's gonna forward the data to the grader agent. The grader agent here is going to verify if the retrieved data retrieved by the retriever agent is valid based on the user input. If it is not valid here, we are going to forward now the user input to another node here, to a query writer agent. The query writer agent is going to take the user input and then generate another input, okay? Rephrase it, create another input that we're gonna forward to the retriever agent. You can see here, once the multi-query agent here, you can see we have here this node, generate here a question. We're gonna forward it again to the retriever agent. Retriever agent feed data, forward it to the grader agent in order to check it. And then here, the grader agent is gonna return here yes or no. If the data is valid, we are going to move here to another agent that allows to generate the response. Okay, generate the response based on the retrieved data. And then here, we are going to move the data here to another agent. Here, we have here another agent. This agent here, the goal here is to check if the generated data doesn't contain hallucinations. Okay, this is the goal of this agent here. Okay, let's say we can get here data in a vector database. Let's say we have here, we have here 1, 2, 3. But the fourth one here is an hallucination based on the user input. Then here, if it contains hallucination here, if it contains hallucination, you can see hallucination, yes. Okay, if yes, we are going to move it again to the generator. The generator is going to generate again another response. And then if it's not here, we are going to move here now we're going to move now to another agent here that allows to forward the generated data to the user. That's how it works, guys. You can see we have here quite a few steps that we need to work through in order to give the user the response. Okay, but this kind of architecture is pretty amazing because it reduces errors. Okay, that's what we're gonna use, guys. Okay, you can see pretty simple, guys. So we're gonna implement this. Okay, and yeah. Alright, guys, now I'm going to show you how to implement adaptive RAG with self-reflection using multi-agent system. Guys, this is the way to implement this kind of architecture. You can use multi-agent system or you can use LangGraph. You can see with LangGraph here, we need to create some nodes. Okay, because here we have some kind of steps from this node to another node. Okay, from this edge to another edge. Okay, that's how this works in LangGraph. Now we're going to build this using multi-agent system, and in here, guys, you have to implement a good system prompt so that it can work out. Now you can see we have here the manage agents, place here the row of the writer agents and hallucination checker agents. And you can see it has here a set tool that allows it to serve the web, to take the data from the internet. You know, the retriever agent here can miss the data in a vector database, and then it's going to inform the reset agent here, and then the reset agent is going to inform the manage agents. We miss data. So if the manage agents get a feedback from the reset agent that it missed data, the manage agent here is going to call here the set tool. And here you can see we have here the planner agents. Once the manage agents receive here the input, first of all, it calls here the planner agents. And after the planner agent, you're going to call here the multi-query agent to create multiple versions of the user inputs. And then it's going to call here the reset agents. And the reset agent here is like the main agents for the retriever agents and the grader agents. First of all, here the reset agents call the retriever agents. And then the retriever agent can use the retrieving tool to get data from the vector database. And once it gets data, it's going to pass the data to the reset agent, And then here, the research agent is going to pass the data to the grader agents. Now here, the grader agent is going to verify the data. It's going to analyze the data if the retrieved data is relevant to the user question. And then it's going to use here some kind of confidence score. If the confidence score is greater or equal to 70%, and then it's going to return yes to the research agents. And then here, research agent is going to give the feedback to the manage agent here. And then it can generate a response to the user. If the research agent here give a bad feedback to the manage agents, the manage agent here, it's going to use a search tool in order to grab data on the internet. You can see it's pretty simple, guys, pretty simple. Now, guys, I'm going to show you how to implement this. We're going to head into the code. And in here, guys, you can see we already passed here a folder. I've already passed here folder adaptive RAG with self-reflective RAG. Here's the folder. And we have here a folder where we pass here the LLM, Supabase. Then we have here sub-agents. We have here the grader agents, multi-query agents, planner agents, researcher agents, retriever agents. Okay. And at the root here, we have the manage agent. You can see in here, I pass here the system prompts that guides the LLM how to do that. Okay, you're gonna read it when you're gonna get the code. Now in here, guys, what I'm going to do in here, I'm going to run this. We're gonna try this. Okay, if I pass this kind of question to the manage agent is gonna call here the C2. It's not gonna call here the planner agents. Okay. Yeah, first of all, it's going to call here the planner agents. And once the planner agent returns here plan, it's going to call now here C2. Let's try this. I pass here what I'm training now in tech. And if I run this, and now you can see actually the manage agent call here the planner agents. The planner agent generate a plan. And then after the plan here, it's going to call here C2. You can see the call here only the planner agents, but also the call here is C2. Okay, you can see. And then we have your data. Okay, you can see in here the manage agent plays the role of the classifier. Okay, it cannot fetch the data in a vector database. It cannot call here the research agents or the multi-query agents for given query. If I pass hello, the manage agent is going to analyze it immediately and then respond to the user. Okay. Now, let me pass here an input like, what is few shots and prompt engineering? Let's see what we're going to get here. And if I pass here, what is few shots? What is few shots prompting? And then let's run this. You're going to see what we're going to get in here. Okay, yeah, let's run this. Okay, let's run this. Yeah, you can see they call the planner agent here, multi-query agents. Yeah, research agents, retriever agents. Okay, yeah, and then here they call here the set tool. It means here the retriever agent gives here a negative feedback. As the retriever agent gives a negative feedback to the manage agent, the manage agent initiates a web search. Okay, you can see the pass here search web. Now let's see at the bottom here if we got data. Let me see here. This is a thinking model. We have a lot of thinking, guys. Okay, we have here thinking. Let me see here the end tag. Yeah, we have here a lot of thinking. Let me see. Yeah, we have here the end tag. Okay, we have here the definition of few shot. Few shot prompting is a technique in machine learning where an AI model is provided with a small number of examples within the prompt. Yeah, you can see the response. Okay, yeah, this is how the system works, guys. You're going to try to analyze it, read here everything. If you don't understand everything, guys, try to refer to this diagram, okay? And here, if you are using multi-agent system, it means you have to know how to craft a system prompt that can guide LLM, okay? And here, once the manage agents receive the user inputs, it's gonna call here the planner agents. Once the planner agents create a plan here, it's gonna pass it to the manage agents. The manage agents gonna call here. It's gonna decide if it's better to call here set tool or to query the multi-query agent. If it's call here the multi-query agents, it's not gonna call here the state2, but instead it's going to call here the reset agent. And once the reset agent finish working, now it can decide if it can call here the state2 or it can generate response back to the user. That's how the system works, guys. Okay, it's pretty simple. You can try to use LangGraph here if you see this is pretty complicated. Now we're going to talk about some cons of the above system, okay? We're going to talk a little bit about some cons of this system, okay? You can see, guys, we just learned how to implement a adaptive RAG with self-reflective RAG. Now, this kind of system that we just implement right here, it has some scalability issues, okay? You know, here we are with this kind of system, we're going to consume a lot of token. And as I said here, a lot of token is equal to a lot of money, okay? Let's say here we have here the manage agents. It's order here the reset agent to grab data. Now here the reset agent, it's gonna forward here the input to the retrieval agent. The retrieval agent is gonna come here. Let's say we free-k token from the vector database. Okay, it has here data. Now it's gonna take here these 2k token. It's gonna pass it to the reset agents. We're gonna pass here free-k token. And what if the reset agent pass here the data again to the greater agent? We're going to consume here again free-k token. Okay, free-k token, something like this. And once it finish here, this agent here, the reset agent, can then forward here this free-k token to the manage agent. You can see we have here a lot of consumptions of token. Now, how to reduce this consumption? Now, to reduce this consumption, we can use here context flooding. Context flooding is a technique where agents offload their memory, offload their context window to a file system. Let's say here we have a kind of system. We have here the manage agents, and here the manage agent here has here sub agents. It is here, let's say it is here another agent here, and here it is here another agent. Let's consider this is a reset agent. It can go on the internet and grab data. Let's say it come here with 6k token. Now, instead of returning the 6k token of data to the manager agent, we are going to take the data, we're going to put it into a file. Okay, we're going to pass the data in a file here. Now, once we pass the data in the file, it's going to give the manage agent a feedback. Hey, manage agent, I keep the data in the file name. It's going to return here only the file name, .txt, okay, is where the data is kept. Now, the manage agent here, it has a tool that allows it to read a file. It's going to use the tool, and then it's going to read the file. Or if it doesn't want to read the file, it can order immediately this agent here. Let's say we have here an FAQ agent. It can order the FAQ agent to read the file, but the manage agent is not going to read the file. It's going to say, hey, FAQ agent, read this file. Now the FAQ agent, it is here too that allows it to read the file. It's going to read the file. And also the manage agents, it can order here, the manage agent can order here this agent to read the file. And once it read the file, it can generate now charts. We are taking this 6k of token and passing it to one agent after another. Okay, this is how we can use context flooding. Okay, context flooding. Context flooding is a technique that allows the agent to offload their memory by using file system tools. Now, in order to learn more about context flooding, you're gonna check this video. You're gonna check the second part of this video. Okay, let me scroll a little bit. Yeah, you're gonna check the second part of this video, guys. Check the second part of this video. Let me select it. You're gonna check the second part of this video, and this is gonna be like the project, because in this video I give you the basic of RAG. Now, in order to improve your level, you need projects. You're gonna check this video. Okay, it's better to improve. And that's all, guys, for this video. I hope you enjoy. Don't forget to subscribe, and I see you in the next one. Peace.